I have been given the unenviable task of talking about coronal phenomenology, which I'm not going to say again. And I say unenviable because there's just so much I could have talked about when I put this presentation together. And I'm sure I'm going to miss out some coronal feature which one of you guys considers as really important or fundamental, and I apologize if I missed it out. And I ask people to keep in mind if I have missed something out and tell me afterwards, and then if and when we run this again, I will be able to improve the presentation next time. I'm going to try and keep it to an hour, and hopefully I'll keep it in time. And if you don't understand what I'm saying, please tell me, and that goes for people in WebEx land as well. I'm assuming people can hear me. Yep, getting us here, which is good. So, okay, let's jump straight in. So, oops, I gotta get it to play. There we go. Right. So begin with what is the solar corona? So the solar corona is basically the outer layer of the solar atmosphere. It is one of its main features is that it's extremely hot. It's 3 to 4 orders of magnitude higher in temperature than the actual visible surface, the photosphere. However, it's something that on a day-to-day basis that we can't see due to the relative brightness of the sun's surface compared to the solar atmosphere. We've had some discussions before looking at the lower solar atmosphere and in particular the white light observations in the photosphere. But just to put it in context on where the solar corona sits, here I've taken like a cutout of the sun and highlighted the different regions, including the temperatures and densities. And I put this up here because it's not possible to dissociate the corona from the lower atmosphere and the actual sun itself. So I am going to have to refer back to some of these regions. I'm not going to give you any of the kind of science behind them, and I encourage you to go away and look it up yourself, but I will have to refer to some of these regions. And I'm sure you're kind of all familiar with the idea in the center of the sun. We have the hot core where we've got fusion processes going on. And then as we move away from the core, we move into the radiative zone, followed by the convection zone. This is kind of a mixing region inside the sun. Before we hit the photosphere or the visible surface, as you would perceive if you were to look at the sun, don't look at the sun, but this is what you see. And then you move into the solar atmosphere, where you encounter the chromosphere, which is the lowest layer, then what we call the transition region, followed by the corona, which basically extends out throughout the heliosphere. If we just focus on the solar atmosphere, here I've got a plot of temperature and density against height, and so the solid line is showing the temperature profile. Oops, there we go, there's my mouse. The temperature profile throughout the solar atmosphere. We see the chromosphere is relatively cool, similar to the photospheric temperatures, and then we see this huge jump in the temperature in the region we call the transition region, and before we move into the corona. Now, the coronal heating problem is one of the ongoing investigations in solar physics and ongoing studies in solar physics, and this is going to be a subject of a later seminar, so I'm really not going to touch on it in this particular seminar, but you should just be aware that the corona is extremely hot compared to the lower atmosphere, but due to the fact that the density is so low, we don't actually see it on this day-to-day basis. So how do we actually observe the corona? I thought the best thing to do is to chuck up a brief history of coronal observations. And again, don't jump on me if I've missed out your favorite coronal observing mission. I'm sure there's other main ones I've missed, but and again, suggestions afterwards for important missions I can include here. So we've been observing the corona all the way back in ancient times through solar eclipse observations, and this was done through in ancient Indian, Chinese, and Babylonian observations. And these have been kind of like ongoing since then, but it's only when we get into the kind of 19th and 20th century that we actually start to make regular observations of the solar corona. And this was firstly done through some kind of spectroscopic and ground-based coronagraph observations. And there are lots of issues with making observations on the ground, mainly related to the Earth's atmosphere, absorption and scattering. And it's only in the 1940s where we start pushing up above our atmosphere. And I highlight here the NRL rocket-based program, where they made some of the first observations from the high above the atmosphere. Then, when we move into the 60s and 70s, we begin to get our first orbiting platforms, and we're able to launch UV and X-ray instruments to make images of the sun in the UV and the X-ray. I'll talk a little bit about why that's important afterwards. Moving on from there, we get onto the first kind of main mission, which is Skylab, which was mission from 73 to 79, which had these dedicated coronagraphs, X-ray images, and UV images on board. In the meantime, the GOES missions were getting underway, and for those who are on the forecasting team, they'll be aware of these plots here, these irradiance or X-ray flux plots, which we actually use for monitoring coronal flares. From here, I want to jump on and just point out the SOHO mission, which is an ongoing mission, which was launched back in '95, and this was a really groundbreaking mission. It had a whole suite of instruments on there. It's been observing, well over a solar cycle now, so we've got a wealth of observations from this particular mission. TRACE, our first high-resolution EUV imager, that was 98 to 2010. And okay, the next mission I want to point out is the stereo mission. This was our first dedicated solar mission that actually looked at the sun from different perspectives away from the Sun-Earth line. So the stereo missions were launched into orbits in front and behind of the Earth in its orbit around the sun, and we got these wonderful images in stereo. And the final image, the final mission I want to highlight is the FBO mission, because I'm going to rely on that heavily in this talk. And FBO is, I would describe it in terms of the EUV and X-ray observations as the next iteration of SOHO. It's got these wonderful high-resolution EUV images on board, and it's capable of taking vector and continuum magnetogram observations as well. I want to give an honorable mention to HI-C, which has produced the highest resolution EUV images that we've actually observed. So there's lots of different instruments out there, and I encourage you to just do a Google search, and you can find a lot of information about a lot of these instruments. So I've picked out a few of the more kind of fundamental images and detectors that we actually use. There are many other ones, but I'm going to be concentrating on these ones at the top throughout this talk. That's mainly because this is just looking at the phenomena in the solar atmosphere in this talk. So firstly, we've got coronagraphs. Coronagraphs allow us to see the solar atmosphere by blocking the bright sun, and we're able to see in various wavelengths, mainly in white light observations. And they're particularly useful for looking at structures or events such as coronal mass ejections and large streamer structures. To actually observe what we would see on the solar disk in the atmosphere, we have to filter out different wavelengths, and we've produced a whole series of images with different passbands, which allow us to see in the EUV and the X-ray the hotter regions of the solar atmosphere. The next one I want to point out is a magnetogram, which I will be relying on a little bit. These don't strictly look at the solar atmosphere, but the solar atmosphere is intrinsically related to the magnetic field in the sun. And magnetograms are very useful for looking at what the magnetic field is doing underneath, and we can see where magnetic fields are emerging or going back into the sun. Down here, I've just highlighted some spectrometers, which allow us to actually look at velocities and densities within the solar atmosphere. I won't be including them in this presentation, but they actually, such instruments actually helped us really kind of understand the actual different kind of structures I'm going to talk about, especially when I talk about densities and temperatures and velocities. Irradiance monitors, so these are very useful for looking at flares, as I said before. And finally, I also want to talk about radio measurements, which also allow us to make the density and velocity measurements. Now, when I was putting this together, I wasn't sure if everyone was familiar with the concept of a passband. So I'm going to chuck up pictures of the sun in different EUV passbands, and I will turn around and say, we're looking at the sun in a particular temperature. And it's not strictly true. So a passband is basically a range of frequencies or wavelengths that can pass through a filter. And so we put these filters in front of our camera, in front of our imager, and we restrict the wavelengths that we actually receive. And in an ideal world, we might have something like a delta function, and then we can specifically say we're looking at a particular wavelength temperature and associate it with a particular wavelength that we're interested in. But in reality, the passbands can be a little bit broader. And so I've put up a picture here of the Proba 2, from the Proba 2 SWAP imager. And we turn around and say that SWAP observes around 600,000 Kelvin. And roughly speaking, that's correct. But if we actually look at the passband, we see this big blobby structure. So it's quite broad. And if we look at the wavelengths, the different lines that we can actually see throughout this passband, there's a couple of different lines in there. So we're not strictly seeing just one temperature and one wavelength. And that's important to bear in mind. And some of the passbands I'm going to show can be quite broad. And so sometimes you will see a feature in a passband which you wouldn't expect to see, because you might expect it to be hot, and we're looking at a cooler passband, or vice versa, and it can actually appear there. In terms of observing the sun in the EUV, we've got this kind of whole raft of platforms and images out there, and I've also chucked Solar Orbiter on the end here, which is going to be going up soon. And so at the top here, I've got SOHO EIT, which first observed the sun in 4 different passbands, and secondly with stereo UVI. All these missions are still going, apart from the Solar Orbiter, which will be soon. And down here with STO AIA, we observed the sun in 10 different passbands, and this is kind of the go-to imager at the moment for looking at the solar disk. At the bottom, I've highlighted the wavelength range that they roughly center on. And as I said before, these can be quite broad. And just to kind of help you out here, these are roughly the temperatures that we're seeing when we look at these different wavelengths. Throughout this talk, I'm going to concentrate on these ones. So these are, okay, the 304, you've got chromospheric, but pretty much the rest of these are all kind of coronal lines. And I'm also going to help you out by putting a number on them. These numbers indicate the temperature in million Kelvin. And I'm going to chuck them over here so that throughout the talk, you can actually have a reference of what we're actually looking at and the relative temperature. And just actually to highlight the passbands, here you can see the AIA passband, and you can see some of them are quite broad. So just bear that in mind. When I turn around and say something is of a particular, we're observing something in a particular temperature, we might have some contamination from cooler lines and cooler structures. Where do these passbands sit? Well, sadly, I've picked this plot here, and most of these passbands are way off this plot here. So we look at the solar atmosphere. Again, we're showing temperature here, so focus on this one here. We've got the chromosphere, photosphere and chromosphere down here. We go into the transition region and chromosphere, where we get the first of the AIA passbands. Then we move up into the 171, 174, which SWAP on Proba 2 and AIA observe, where we see just above what we call the transition region. And the rest of these lines are really hot and beyond this plot here. Now, it's customary when we talk about the solar corona to divide it into broadly different regions. And so here I've just grabbed a 193 angstrom image from SDO, because this is a really good passband for seeing cooler and hotter structures. The first thing I want to point out are coronal holes. So we've got different coronal holes in the sun. We have these kind of like polar coronal holes, which we see at the top and the bottom, and these evolve through the solar cycle. They get bigger during solar minimum, and they disappear around solar maximum. And also around this center as well, we can have these coronal holes appearing here, and these also kind of move around throughout the solar cycle. Next thing we want to look at are active regions. So these are bright, hot regions that we actually see here, these very dense magnetic structures. And the quiet sun region. So pretty much people defined the other regions and then said, what have we got left? We will call this the quiet sun. So that's what we see here. Now, I'm going to talk about these regions in a bit more detail in a second, but it's at this point I have to make a segue and talk about coronal loops. And that's because coronal loops are the fundamental building blocks of the solar atmosphere. They're prevalent throughout active regions and the quiet sun, and you'll see a little bit later they're hotter in active regions, but they are small loops are interspersed all throughout the quiet sun. So where do these guys come from? So magnetic fields are actually believed to be generated at the base of the convection zone. So here I've chucked up my image of the solar interior again, and we see the convection zone here. And this is a region where there's all kind of like churning plasma inside the sun. And the magnetic fields are generated through the change in the fluid flow velocity across this layer. And the field lines are subsequently stretched and concentrated, and the field strength is kind of amplified through these plasma motions. And this is like induces electric currents throughout the layer. And the generation of the magnetic fields within the sun actually leads to the emergence of magnetic flux at the surface. And the emerging flux has this form of flux tubes. If people are interested in this, it's quite interesting to actually look at some of the physics behind magnetic buoyancy and how these regions actually pop up through the surface. Okay, so how do they appear? Well, these loops appear there. They've got a whole range of sizes. I've taken an image here from Trace, which really kind of like highlights these magnetic field structures. And I just want to point out that what we actually see when we look at these images, we're not seeing the magnetic fields. We're actually seeing the bright emission from plasma that's trapped on the magnetic fields. As though there's probably fields here that we can't see because there's no plasma on them, and I've got a particular passband here. There's probably hotter loops and there are cooler loops. But if I talk about seeing loops, I'm talking about the plasma that's trapped upon them, and we see these kind of like nice loopy structures. And there's been various models actually made to actually look at the coronal field structure, and I've just grabbed a couple here. We've got a magnetic extrapolation model from Shriver et al., which kind of shows this hairy ball. This is just showing some of the larger field structures emerging from the sun, and just showing how complicated it is, and the different sizes of the loops. And over on the right-hand side, I've got a model from Title et al., which actually shows a smaller scale image. And again, we can see all these kind of magnetic structures coming through the solar surface. As I just kind of highlighted, these loops come in a range of sizes. I've got like an arcade of loops here, and just grabbed this from the internet just to show where the Earth, the scale on there. This is like some of the larger loops we can see in the solar atmosphere. But generally, these loops are believed to be made of smaller strands, and loops can go all the way down to a few megameters. And a couple of years back, I think it was the Marshall Space Flight Center, NASA, MSF, they launched the High-C mission, and they produced some of the highest resolution images of the solar atmosphere. No, these are the highest resolution images of the solar atmosphere. And here up here, we can see an AIA full disk image, and they focused on this region here, which is what we're looking down here. And I'm afraid this projector here doesn't do them justice, but we can really see some of these small-scale loop structures. They looked at these loops, and they found that they had roughly constant temperature distributions across their width, and they believe that we're actually getting down to the kind of fundamental magnetic loop size in these observations. So normally the bigger loops are believed to be composed of lots of smaller strands, smaller loops, but they believe in these observations we're seeing the kind of fundamental loop size here. Just to say that we're observing here around 1.5 million Kelvin, and the loop lengths that we kind of see here range between around 1 megameter, and they have thicknesses of around 200 kilometers. And I've got a nice movie here which I just wanted to put up, which Barbara gave to me kindly. And this is showing the corona through various UV band passes. We've got a magnetogram in the top left, and we've got a more photospheric chromospheric line on down here at the bottom left here. And here we can see coronal loop structures off the solar disk in various temperatures. And what you can see is you can see these loops in all the different temperatures, which shows the range of temperatures going from around 10 million degrees all the way down to the chromospheric temperatures here. So these loops are spread throughout the solar atmosphere. Sometimes we can see them, sometimes we can't, sometimes they're bigger, sometimes they're not. But they're the fundamental building blocks of the solar atmosphere. Now I want to jump back into different regions. I'm going to focus on active regions. And you can already see from this picture here, if you look at this active region here, this bright blob here, you can already see some kind of like loop structures in here. These are really kind of hot regions that we're kind of interested in. And I've just taken a movie here of this active region. I think this is from last week and a few days earlier. So here we can see the active region here on the disk, and from a few days earlier, this is what it looked like when it was on the limb. So you can kind of like make out, sorry, it's down here. You can make out some of these loop structures here and over here as well. And we had a talk, a seminar earlier, which focused on sunspots. And sunspots you can find underneath these regions. So the magnetic fields are basically coming from below. They're coming through the solar surface, and they're going out into the corona, where they're kind of looping over and going back again. And if we actually look at a magnetogram of this region here, we see this kind of like nice bipolar region here. And just to highlight, in these images, the black is showing magnetic fields pointing away from us, and white is showing magnetic field lines coming towards us. So you can imagine the field structures coming up, looping over and going back down. And if I use some opacity and chuck a 193, 195 angstrom image over the top, you can kind of just about see, where's my mouse pointer? Lost it again. We've got the two directions of the magnetic field, and we can see the loop structures over the top connecting these two regions. And so what we find is, because of the bipolar nature of active regions, they're kind of these closed magnetic field regions, and due to motions below, these magnetic fields can get wound up, and through processes such as magnetic reconnection, which I will briefly talk about later, and wave motions and things like that, we actually get significant heating in these regions, and that's why they appear as these very bright structures. What else do I want to say? Okay, I'm just going to jump through what these guys look like in the different passbands again. So again, we can see these active regions. They're very hot regions. We see them all the way up to this 10 million Kelvin. And then if we jump down, we go down to 6 million Kelvin, we can still see them quite brightly, 2.5, 2, 1, and then we can see them really clearly at around 600,000 Kelvin, these wonderful kind of loop structures here. And just to show what they actually look like in more of the kind of chromosphere, where they're still kind of emerging out, we see that this is a smaller region, and we're looking more at the kind of the foot points, or towards the foot points of the active region here. Now, okay, question? No? Okay, right. I just touched on magnetic reconnection. There are various ways that the solar atmosphere can actually be heated, and how active regions can be heated. but one of the main concepts I've got to get across is magnetic reconnection. And so what we have is the solar atmosphere is composed of these magnetic structures, and the foot points of these magnetic fields can actually get twisted around. And what happens is the magnetic fields get twisted around, the flux tubes get twisted around each other, and this creates localized current sheets. I think we're going to have a talk later on about MHD and things like that. Okay, so some of the more fundamental concepts might get covered there, so it's going to be more of a hand-wavy description here. But field lines can get twisted around each other, current sheets can build up, and what happens is we can get into situations where if we wind up the fields enough, they're somehow able to break and reconnect in this process we call magnetic reconnection. And this liberates energy from the current sheets in the form of thermal energy and kinetic energy. And this is a very idealized kind of cartoon here, which is showing two fields getting kind of twisted around each other, and then they're breaking and reconnecting. Think of it like elastic bands getting kind of twisted up, and then they break at some point, and they're able to connect back together. And this is believed to be one of the fundamental ways that the solar atmosphere is heated, which again will be covered in a later lecture, but also one of the main reasons why active regions are hot. And it's also through this kind of reconnection process which can lead to active regions producing flares and eruptions, which flares I'll talk about a little bit later, and some of you are probably familiar with them, and same with CMEs as well. Okay, so just bear that in mind. That's what magnetic reconnection is. It's the breaking and reconnecting of the magnetic fields. Now, jumping back into our regions of the sun, we're focusing on the quiet sun and coronal holes. I'll kind of lump these two regions together. It's probably unfair of me to do that, but here we can actually see a very nice kind of polar coronal hole extending down to low latitudes. This was taken quite recently, and due to our period of the solar cycle, we can see these extended coronal hole regions right now. So the coronal hole are these relatively dark regions of low here. They're described as being open field regions. So before I talked about how the quiet sun and active regions are comprised of these little structures, where we basically see the field lines coming up and going back down, and these are called closed field structures. In the coronal hole regions, they're often described as open field regions, or regions where the magnetic field connects a long way away from in the heliosphere. And what happens is, as these regions are mainly open, it allows the plasma that's emerging from below in these regions to actually escape freely, and these regions are associated with the fast solar wind streams. So any forecasting audience will be aware that whenever we see a coronal hole align magnetically with the Earth, we experience fast solar wind speeds, which can actually increase geomagnetic activity at the Earth. As I said, these structures are relatively cool compared to the rest of the solar atmosphere. And if we actually jump into some of the hotter passbands here, we can see the coronal holes largely kind of disappearing. And again, if we go down to cooler and cooler passbands, we start to see them around 2 million degrees here, and that's just due to the lack of emission, due to the plasma actually escaping from these regions here. In the meantime, I just want to point out that constantly in the background, we see the quiet sun as this kind of like continuous emission here. And this is related to coronal heating, which will be covered later. And there's some kind of fundamental process going on in the background that's able to heat the corona to these really high temperatures continuously and across the entire solar atmosphere. So as we go down towards the cooler passbands, it's not so clear in the around 600,000 Kelvin due to obscuration. And again, we see it here as we move down to the chromospheric regions. So I've touched on it a little bit about, talked a little bit about the solar cycle, and I've grabbed this picture here, which is from the SOHO EIT mission. I think this is 26 angstroms, I think. Yep. And what I want you to take away from this is that how the sun is actually changing across the years here. So going from solar minimum to solar maximum. And what we actually see is, we see as we progress through the solar cycle, we see the coronal holes kind of getting smaller, and we see more kind of active regions emerging. And as we see more active regions, these are regions that produce a lot of solar activity. There's a lot of churning of magnetic fields and energy being released through flares and CMEs. This is related to the number of sunspots as well. So we see increased number of sunspots when we see increased number of active regions, or vice versa, so I should say. And what we basically see is we see the solar activity go through this magnetic activity cycle of going from what we call the quiet sun, when it's relatively quiet. There's not many active regions. There's not many flares. There's not many CMEs. And then as we move to more active periods, we see more active regions. We see more energetics actually happening. And this is fundamentally related to the magnetic field. And so I've just grabbed this, this nice image that somebody made, which shows photospheric magnetograms. And once again, this is around like solar minimum time, where we don't actually see many magnetic structures on the sun. Either end, these were probably from the peaks of the activity cycle, and we see a lot of these magnetic structures here. So the magnetic field is getting wound up and releasing energy around these periods. Now I want to I've talked a little bit about the regions of the sun. So we've got active regions, we've got the quiet sun, we've got coronal holes. I want to talk a little bit about some of the more kind of transient features that we see on the sun now. And I want to focus a little bit on filaments and prominences, which confused me for a long time because I thought they were different things. But they're pretty much the same structures, but they're labeled differently depending on whether they're seen on the solar disk or on the solar limb. So here we can see this magnetic structure on the limb here, and we see the same, roughly the same structure here, and this is a few days later. And at the end, there's some kind of activity where it becomes unstable and actually erupts. So a prominence is like a large, bright gaseous feature extending out from the sun's surface, and it's often seen in this kind of twisted loop shape. And they're anchored to the sun's surface in the photosphere, and they extend outwards into the solar corona. Now, while the corona consists of this kind of really hot ionized gas, the prominences actually they're a lot cooler than the solar atmosphere that we normally see, and through this kind of cooler temperatures and through some absorption features that actually appear darker relative to the rest of the solar atmosphere. These structures can actually persist on the sun from days to months, and they can be extremely large structures. They can be thousands of miles. They extend thousands of kilometers out into space. And what happens is sometimes they can become unstable. And what we find is they kind of break apart and actually give rise to coronal mass ejections. Or this is one way we can actually produce a coronal mass ejections. And it's still an active area of research trying to understand how and why these prominences actually form. So what do they look like in the different temperatures? As I said, they're relatively cool structures. So this is what they look like here in the cooler one. Oops, and if I go to the hotter one, we really can't see them so well in the hotter band passes. And as we progress down through, we'll begin to see them as we reach the kind of cooler band passes of the solar atmosphere. And then we see it quite clearly in the kind of chromospheric lines here. And I just wanted to show quickly what an erupting prominence actually looks like. And so here we can see one off the edge of the sun here. Now there's going to be a dedicated session talking about coronal mass ejections, I believe, I hope. About the heliosphere. So I don't know if this is going to be covered more or not, but just to say that we see these erupting structures, which we can actually trace all the way out, and if they're orientated in the right way, then they can actually come towards the Earth and interact with the Earth system. So Elena's just saying this particular eruption could possibly be a failed or partially failed eruption where we can actually see a lot of the material returning back to the sun at this lower foot point here. It probably is, but I just grabbed this from the internet just to show what an erupting prominence actually looks like. Okay, next, solar flares. So again, forecasters are going to be familiar with these things here. So these are, a solar flare is this kind of like sudden flash of increased brightness, and normally, usually observed near the actual solar surface, lower down in the corona, and they're sometimes accompanied by eruptions of CMEs and post-flare loops and EUV waves and a whole menagerie of different coronal features. And solar flares are produced by the release of magnetic energy. And we believe that this is fundamentally related to the process of magnetic reconnection, which I touched on earlier. So remember the twisting up of the magnetic fields. The fields are able to break and reconnect, and as they do so, they release a lot of energy in a quick, impulsive event. And what I'm showing you here is a plot from the GOES mission. This is the GOES X-ray flux. And so it effectively looks at the sun as a star. So it's taking the emission across, the X-ray emission across the whole sun. And what we can see is we can actually see here in this plot here, we've got some kind of like the X-ray flux of background levels, and then there's a sudden release of energy here. And this is the kind of traditional picture of what a solar flare looks like in the GOES X-ray flux. So how do these events occur? As I turned around and said before, as I said before, the magnetic fields get mixed up. There's magnetic reconnection, and this is kind of just a cartoon again that I grabbed from the internet, which shows there's some kind of magnetic reconnection going on here. And then from this, we get electrons and radiation accelerated from this region as their energy is liberated. We see flows of energy down towards the lower solar atmosphere and the chromosphere, where we can get other emissions such as hard X-ray and gamma rays and things like that. And we see post-flare loop systems forming down here, and quite often we can also see coronal mass ejections ejected from the actual flaring region. Now, forecasters will be, space weather forecasters will be aware of this energy scale here, which is the GOES classification of solar flares, which they classify going from A, B, C, M, and X. I don't know why that was chosen. I'm sure some people here know that. But anyway, X are the most energetic flares, and these are like the big suckers that we're afraid of. That if a really big event happens, and it can really affect systems in orbit due to the amount of energy that's released. And but when we look at the solar atmosphere, we also have to consider smaller flares as well. And these are flares known as microflares and nanoflares. And so here I've just made a quick plot which shows the power spectrum of flares versus energy. And what I want you to take away from this plot here is we have lots of flares with lower energy and with less flares of higher energy. And what is actually believed is that there are various ways that the solar atmosphere might be heated, but one of them is it's believed that very small solar flares could be one of the actual phenomena that's actually heating the solar atmosphere. So if you imagine this plot here, we have very few X-class flares down here, and then as we go down towards C-class flares, we see them on a daily basis. And then if we actually look at less energetic flares, we get more and more and more of them, until we get down to what we call the nanoflare scale, and we believe there's lots and lots of nanoflares occurring at any one time. and these are actually able to heat the solar atmosphere. So you can imagine magnetic fields always reconnecting across the solar surface and actually able to heat the atmosphere. I'm not saying that this is the only way the solar atmosphere is heated, but it's probably one of many. And it's just, we observe the big flares, but we have to understand that on this scale here, there's lots of smaller flares going on that we don't actually see on a day-to-day basis. And I grabbed this plot here, which is showing the average monthly sunspot number, and it's got the flare magnitude plotted on the same plot here. And I just want to highlight the solar activity cycle again, which is this magnetic cycle. And what we find is during periods when we have sunspots, and therefore more active regions on the sun, we've got more of these active regions twisting and breaking and releasing energy and producing very high energy flares. And so what we see here is we've got like these X-class flares up here, the powerful ones. When we've got more sunspots and active regions, we've got more high energy flares being released here. So we do see this kind of like variation in the larger flares throughout the solar cycle. But the solar atmosphere is always hot. And so there is some kind of like fundamental mechanism going on all the time on a smaller scale that's able to kind of maintain these temperatures. What do these flares look like? So here I've grabbed, I think this was the X-class flare earlier this month. It wasn't the biggest one, it was the one just before because it was closer to disk center, so it was more interesting to look at. And so this is what I've shown you, this kind of like goes light curve before, where you see this kind of sudden release of energy. This is what it actually looks like in 193 angstroms. And then if we look at all the different passbands, we can see that these flares are releasing energy at a whole range of temperatures. There's a scale of energy scale that these guys are actually releasing energy here. So we see the flare in the hottest band passes all the way down to the coolest ones here. So following flares, as I said before, are kind of associated with a number of phenomena, including coronal mass ejections, which I'll touch on briefly afterwards. They're also related with EU waves and coronal dimmings, which I'll also talk about later, but also structures known as post-flare loops. So we're going back to loops again. And yeah, so this is a very large post-flare loop system, which was seen by the Proba 2 SWAP imager, and it was the largest post-flare loop system that we've seen in the last solar cycle. And if I just quickly throw this image back here, our flare is kind of going here, releasing energy. We're getting accelerated particles and field lines, new field lines being kind of generated down here, and sorry, the reconnected field lines are down here. And we're actually seeing these field lines getting heated by these accelerated particles and electrons from this region here. And they generate these post-flare loop systems. And so here there was an eruption and a flare just behind the solar disk. And we see this post-flare loop system growing out here. And we actually look at the flare profile here. The original flare is the original release of energy during the flare was right here, and it's actually quite small because it occurred behind the disk. But when we see this bright emission here, we're actually looking at the post-flare loop system that's actually growing. And so sometimes when we see these kind of prolonged flare events, we're actually seeing emission from the loops which are generated after the flare and after the coronal mass ejection. And this is from accelerated particles coming from the flaring region and ongoing magnetic reconnection. So these post-eruption loops or post-flare loops are kind of seen as these hot arcades, and they've been seen to grow to heights of 10 to the 5 kilometers. And these observations, which I'm highlighting here, were the highest structure, the largest set of loops that we've seen in the last solar cycle. So I focused so far on disk structures, and I'll come back a little bit later to look at EUV waves and coronal dimmings. I quickly want to jump over to off-limb structures. This is mainly because Marilena told me to do this. No, I had to have this in there. Okay, so so far I focused at what's happening on the disk, but we've had chronograph observations for a long time now, and we've been able to see a lot of these structures on the disk extending out through the corona into the heliosphere. And this is an image I grabbed from Stanford Solar Center, and I'm not going to kind of read through everything on here, but we can see prominences coming off of sort of this. I think this was actually made by Shadia Haval. This is an eclipse observation that she made from the ground. Here we kind of see the what I'm calling what I call the extended kind of corona here. We see these wonderful streamer structures, and these are these kind of large cap-like coronal structures with pointed peaks, which are created by the expanding solar atmosphere, kind of dragging out the field lines and the emission. And they're often overlying the active regions that you saw on the solar disk. And they often have the prominences and filaments at their base. We can see polar plume regions. We've already touched on coronal loops and their different sizes, and we can see some of these coronal loops extending all the way out into the extended corona down here. And again, up here in this particular plot, we can see some nice prominences out here. So just bear in mind, I mean, the sun is occulted here, so you're looking at 3 to 4 solar radii out here. So some of these structures are extremely big in this image. And another cartoon I've just grabbed from the internet just to show, just to perhaps highlight some of the magnetic structures that are underlying these, sorry, the magnetic fields that are underlying these structures. If we jump backwards and forwards, we see like some of these streamer structures over here extending out. We can imagine the kind of like magnetic field lines that the plasma is trapped on extending out here. And the other thing that I should highlight from this image here, we actually see some coronal hole regions. I imagine this region here is probably like this kind of a little bit darker region here is highlighting a coronal hole region here. So if we were to look again at the magnetic field structure, we'd see these magnetic field lines extending all the way out into the heliosphere. Now, in terms of off-limb structures, off-disk structures, one of the most prominent events and structures we have to consider are coronal mass ejections. So I've talked about prominences and active regions and flares, and a lot of these structures can become unstable as the magnetic field becomes tangled up and reconnection occurs and energy is released. And so what happens when these structures erupt? If we actually look in chronograph observations, what you're seeing here is an AIA image, so an image looking at the solar disk in the center here, and then over the top here we're seeing a LASCO white light image. And this is actually related to the very long post-flare loop system that I showed you earlier. So there was a flare that occurred just behind the solar disk in this particular case, and it produced this large coronal mass ejection. Now, these CMEs are often associated, as I said, with prominences and filament eruptions, but also with solar flares. And we're still looking into how they're actually related to each other. Basically, big arguments in the past on whether CMEs cause flares or flares cause CMEs, but they're all one of the main thing, and we're seeing different aspects of the same thing here. So we see the kind of massive CMEs moving off from the sun, and if they're located near the disk center, so pointing towards the Earth, from this viewpoint, then we might actually see effects of the CME at the Earth. And just to get a more kind of contemporary observation here, on the left-hand side here, you can see a very small eruption that occurred off of the east solar limb. Just jump back there again from last week, I think this was there. But what we do is, as you can see here, it's quite difficult sometimes to actually see these eruptions in straight images. So we perform a process known as differencing. There's various ways of doing differencing, but in short, where we subtract one image from the previous image. And what we're able to do is we're actually able to highlight these actual eruptions here. So if I jump back here on the right-hand side, if you look at the difference image, you can clearly see this coronal mass ejection moving out. And this is probably going to be covered a little bit more in the heliospheric talk that's coming up, and where the different structures inside the CME will probably be covered. In terms of the lower solar atmosphere, people are interested in how CMEs are able to erupt. And yes, we've got this kind of like this concept of the breaking magnetic fields releasing energy, but there are different theories and models that are being introduced as to how these events can become so energetic. There are some people who believe that we can get reconnection instabilities in the lower atmosphere, which is able to release material above, and then there are other models where we have reconnection occurring above structures in the solar atmosphere, and by reconnecting successive field lines above a very buoyant or energetic structure, a CME is able to escape. And I'm sure that we'll find in the future, as we continue investigating these things, different CMEs will be caused by different mechanisms. Now, I've talked a little about flares and CMEs, often associated with them on the, again, in the lower coronal observations. We also see structures known as coronal dimmings and EUV waves. So I will show you what one of these things look like. So I grabbed this from Solar Demon, which Emil's in the audience here. This is a wonderful, I've linked it down here. It's a wonderful web page where you can go online and actually see, oops, I'll skip now, I don't want to do that. Where you can go online and you can actually see a whole catalog of EUV waves and coronal dimmings. And so again, we've got a different image here of the solar disk. So we're looking at around 2 million Kelvin solar disk here. There was a CME and a flare associated with this event. So at the beginning, there's a bright eruption. And firstly, I want to point out here in the center, you see these kind of dark regions here. So this is what I call a coronal dimming. And this is a region which it appears dark, but it's effectively cool compared to the other ones, but it's also cool compared to what the sun looked like before. So when we make these difference images and we subtract the background image, these regions appear dark. Secondly, I want to highlight this wave structure, which is moving away from the active region as well. So these are called EUV waves. They're often associated, or they can be associated with Morton waves lower down in the solar atmosphere. And the fundamental nature of these waves is not fully clear, and there's still some kind of arguments going on as to what's their cause and whether there's two parts. And actually jump onto the slide here before I say everything that I want to say on here. And so what do we see when we see these EUV waves? Well, we see these kind of transient moving fronts of increased emission in the EUV. They have velocities ranging between 100 and 500 kilometers per second. They often originate from active regions. And normally, if there's a flare or an eruption occurring, we'll see these events. And again, we see kind of the dimming regions in here as well. They're often within the EUV wave, although there is some kind of discussion on whether the EUV wave or the dimming lead each other. But personally, I believe the EUV wave is is outside of the actual dimming region. Often when we do see the dimmings, these dark regions in the middle, we see an associated CME, which leads to some people thinking that some of the mass that we see in CMEs may be coming from these dimming regions, although this is kind of like a contentious area of research at the moment. What else can we say about these things? Again, the physical nature of the EIT waves, or EUV waves, sorry, I switched between the two. They were first observed in the EIT instrument, so sometimes they're called EIT waves, sometimes they're called EUV waves. But anyway, there are various theories as to how these waves are generated. Some people believe that these are fast mode waves. There's been ideas of these successive opening of magnetic field lines, or we've got some kind of successive current sheet heating going on. Now, and some people believe that there could actually be two components going on, or blast waves is another very, very kind of popular theory behind these things. But we don't fully understand what's actually driving or generating these waves, and why we don't always see them. I just want to grab a set of stereo observations here. So this is at a slightly lower resolution than the AIA images that I've been showing you. But this was an event that occurred in 2009. There was a CME, which you will see down here. This image is showing, this movie is showing a LASCO, sorry, a Core 1 coronagraph movie overlaid on a UV image from stereo. I think this one's A, I'm not sure. One's A and one's B. I forget what the orientation was. But anyway, what we saw was we saw this flare in CME from at disk center from one perspective, and we saw it on the limb from another perspective. And this plot up here is just showing where the sun is, where the Earth is, where stereo A is, and stereo B is. And so you can see they're roughly separated by 90 degrees. So this event occurred disk center in one, observed by one satellite, and on the limb when observed from the other satellite. And what we see is we see this CME moving off on the limb. And if you look carefully in here, you can see the UV wave, first of all, moving out. And you can also see the dimming close to the limb here. And on the disk, similarly, we see the wave moving out. And you can see the dimming here as well. So we see these phenomena from when they're on the disk, in the central disk, and on the limb. And it's these kind of observations that led people to believe that the dimming is largely the kind of footpoints of the CME, and perhaps somehow related to the mass loss in the dimming is related to the mass that's in the CME. Still not 100% clear on how these things actually fit together. So I just want to finish with this very nice plot from 1997 made by, this movie made in 1990, from some data from 1997 made with EIT in the 195 angstrom. This is like one of the first most prominent dimmings, which was studied in a series of papers by Barbara Thompson. And what we see is this eruption here, and we see this wonderful kind of like bimodal dimming event here. Yeah, okay, I think I've said what I want to say there. Okay, I just want to highlight what they look like in different images. Their sizes can be up to a quarter of a solar radii, so these can be really kind of big structures. And as I said before, they're often associated with CMEs, flares, and EUV or EIT waves, depending on which name you like to call them. And there's some evidence that they're actually a tracer of coronal mass ejections. The dimmings are relatively long-lived structures, and so they occur and they can be seen from hours to days. And this could be related to whether the dimmings are still connected to the eruption that they were associated with, and perhaps if there's still the opportunity for emergent flux to escape, and they could therefore remain darker longer, a bit like a coronal hole region. You've got material that's able to escape into the outer solar atmosphere. Whereas if they kind of recover quickly, so we see the dimming disappear quickly, we could be seeing a more kind of confined case. The recovery is, again, not fully understood, but there's kind of various research actually going on here looking at how coronal dimmings recover following an eruption. And just to say that we actually see the coronal dimmings in multiple temperature band passes, which is kind of indicative that it's actually a actual mass loss rather than some kind of temperature shift. So we're not heating a whole bunch of material up and moving it out of our bandpass. So I think I'm close to an hour already, actually. So I'm going to call it quits at this point. I apologize if I didn't include any, something that you're all interested in. I've got like some suggested further reading things up here, which, you know, there's lots of things that I could cover, and I hope I made some sense. This was, you know, this is like a broad subject, and I'm happy to take questions, and I'm also happy to take suggestions for next time. This is the first time I've done this. I've never taught classes or anything, so it might have made any sense at all, in which case send me a polite email telling me that, and I'll try and do better in the future. Thank you for listening to me.